How's it going, Sarah?
How are you? Oh my God, you're at work.
Yes.
That's amazing.
I had to make a couple runs. Yeah. It took a long time to figure it out. I had to go to Best Buy twice because I had to get the HDMI and then I had to get another USB hub. Such a
Nothing from
Such a pain.
Space?
no,
That's what I figured.
nothing.
You want to take a Tenets or did you do that?
No, not yet. If you just the one thing I was pull it up on your Excel.
Yeah, I'm just gonna do Google Sheets and then I can just share it with you that way.
Yeah, awesome.
Okay, that's good.
So this is Sarah. She's a president of SOGIS.
Hi, everyone.
Are you guys also a part of SOGIS? Kinda, yeah, a little bit.
What year are you guys?
I'm in second year.
Oh, you're my year.
Oh.
You guys?
Pretty cool.
Okay, it's just gonna do it.
Yeah, no worries.
And I'll get
No worries. We're gonna give some time. I think we're gonna start around 12:10. So
that. Okay, perfect. I'll be right back.
okay, awesome. Cool. Okay, the Zoom's getting filled out now, so more people are coming up. So how are you guys finding comp sci at Gulf so far? First year, pretty exciting, right? Who crazy? Yeah, who are your profs? Oh wow, those are good ones. But you didn't get Deb Stacy. That was my first year prof. She was a little tough. You'll get used to her in the future, I think. She does a lot of teaching. That's cool. So where are you guys from?
I'm from Milton.
Milton. Okay, I'm from Mississauga, so not too far off. Awesome. Okay, I'm gonna go run upstairs and see if there's any people at that door. Wait 1 second.
Okay, I'm gonna grab your first name, last name, and any contact. It's just for COVID and for attendance. For this thing, so Convolutions. Hello. How are you?
I'm good.
Thank you. G-A-V-I-L. Last name? And what's your contact? You know, so you yeah, they're just like the last name. And anything? Yeah. And does it just devise that result? How many people are online?
We have right now 12. 12. So there a lot of people are coming in on the Zoom.
My name is Faraj, Farz, and surname Saudagar, Saudar.
Okay. I'm going to admit everyone else in.
Oh, do you want me to?
Zoom is in.
FAR. Yeah,
It's okay. All the information will be there.
Do you want me to go into the Zoom meet and then keep track of all the questions?
That'd be good. Yeah. Yeah. That's one of the things. Okay. Awesome. Okay. Welcome everybody on Zoom. Let me know if you can hear me. Just give me a little thumbs up in the chat. We have 13 people right now. Okay. Awesome. Sweet. Okay. Awesome. Thank you very much for coming down. We're going to start very soon. Great. Awesome. 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 Okay. Okay. Cool. Perfect. Yeah, it's actually on, you go to bit.ly/break. Or if you just check out the Instagram, there's the link there. Okay, awesome. I am going to start off. If some people join later, that's no issue at all. Okay, perfect. So let me just start off with saying, thank you everybody for coming in today. We have a few people down here in the basement, in the Reynolds building, University of Guelph, working hands-on, and we have even more people on Zoom. And I gotta say one thing, you guys are awesome for coming down on a Saturday, a rainy Saturday, walking all the way down here, getting in the Zoom to learn some things when no one asked you to, okay? I think that's really great, and I think you should really look forward to the type of stuff that we're doing here. My name is Nick Vinden. I'm a third-year student here at the University of Guelph. I've been interested in deep learning and machine learning for a very long time. My first algorithm I made was in grade 11, and I've been chasing that ever since, and now it's completely consuming my life. I used online courses and materials to familiarize myself with the topic, and I extended that into getting research positions at the university. I've worked with Dr. Neil Bruce. If you haven't heard of him, I'm sure some of you have had class with him, working on image recognition and something called scan path analysis. I've also worked with, sorry, I'm gonna let some people in. I've also worked with, if you've ever had Louise Antoine as a professor, I'm working with her currently, trying to publish deep learning papers on something called name entity recognition. So I've been in the scene a while, and from that, I really figured out that it is really tough to get into machine learning and specifically deep learning. There's a lot of hurdles to overcome. And so I've tried to put together this course to really let you guys excel in the field and get your first step in. What I'm trying to do here is I'm trying to make a collaborative workspace. So at any time in the chat, please make sure to ask questions. If you're here, just yell at me. I think learning should be a collaborative effort. So if there's someone, I think someone has their mic on, and just be careful of that, okay? I think learning should be a collaborative effort. So please, let's talk. We'll have an open discussion, especially at the end of this course when we really start coding. That is when we can really have a communication. Okay, so awesome. One thing I'm going to say right now is that we have the room for 3 hours, but the course I developed and designed it to be about 2 hours, 2 hours, 15 minutes. So if you need a ride or anything, if you need to call your parents or anything, figure that out, let me know. But I will be here until the end of the class. If you have any questions or if you want to talk about some material or anything in the future, I will be here. Okay, awesome. Let's get started. Unfortunately, right now, the presentation mode is a little bit buggy when I'm using, I have to use this camera and also presenting on these screens. If I present, it kicks a lot of people out. So right now we're trying to deal with this right now. Okay, so here is the introduction. Okay, so this is Brain Tank. Welcome, this is week 1. It's an accessible deep learning workshop. So the first question I'm going to ask for you right now is, why should you care about deep learning? Okay, it's a profound question, and for me, it has a very simple answer. You just take a look at what it can do. Okay, so first of all, what you're looking at right now are some slides of cancer cells, benign and malignant tumor cells. And in the past, it was a doctor's job to diagnose them as positive or negative. And we see on specific skin cancer cells, doctors can find about a 65% accuracy rate. Researchers at the Northwestern University of Feinberg School of Medicine have developed a deep learning algorithm to boost it up to 95. Okay, that is profound results. It is directly saving lives. And it's a technology you could not have done 10 years ago without the advent of deep learning really exploding. Tesla, I know you've all heard of the company. Saving lives on the road. Each year, millions of lives are lost from human driving errors. We're talking about drunk driving, distracted driving, human timing error, and needless collisions are caused. So right now, today, the Tesla autopilot service has a better success rate driving. And tomorrow, it'll be even better. Yet another advent that was impossible without deep learning. It's these deep learning algorithms that are driving technological change like this. I've talked a little bit about this before, especially if you've been keeping on with BrainTech's Instagram, but protection of the truth. We are seeing more and more different politicians, leaders, influencers able to use purposely misinformational speak and dialogue to make public opinion sway in an unfavorable way and in a way that's not truthful. We have companies like Fakebox and Machinebox working towards trying to find solutions that look at the natural language, spit it out in articles, in press conferences, in text, in tweets, to find truth behind it. Okay, so we have very real practical purposes to getting deeper, and we're able to solve problems we weren't able to solve 10 years ago with these deep learning techniques. So I talk about artificial intelligence, machine learning, and deep learning a little bit interchangeably. Those are different terms, and we're going to go over a little bit what it means, because right now you guys are sitting in a deep learning workshop. We're going to go over what exactly that means. So if you've ever seen a chart that looks a little bit like this, you can see that deep learning is a subset of artificial intelligence and machine learning. If you look at the definitions a little bit, artificial intelligence is defined as a science devoted to making machines act like humans. It's very general. It's been around for a long time. Since the advent of computation, we've wanted machines to do things that previously only humans could do. So looking at some examples, what you're looking at the top left is a tic-tac-toe bot. It's a machine. You might have actually developed this in a class at Guelph if you were here at the University of Guelph, and it is unbeatable. It's designed so you cannot defeat it. What you're looking at the bottom, I'm sure a lot of you guys have played something like Mario Kart, and I'm specifically talking about the CPU computers that you can race against. Both of these challenges are a type of artificial intelligence. They use procedural code that the human brain develops, and you put it into the system to mimic human-like behavior. Okay, so if you're trying to make a tic-tac-toe bot or computers in Mario Kart, you're sitting down and you're tackling the challenge a lot like you tackle one of your assignments. Okay, you're sitting down, you're thinking, if this, then that. How can we tackle this problem? Maybe in tic-tac-toe, we can use different types of data sets and ways of solving it in different routes. In Mario Kart, what happens is they use computers to follow specific tracks in the trail, predefined by programmers. It's very procedural, using if-then statements, and you're getting to a solution very traditionally. with what you're seeing right now, this is IBM Deep Blue, which is a chess robot developed in 1997 to defeat the best chess player in the world, the name Garry Kasparov. You can see right now, if your professor gave you a assignment to make a chess bot to beat the best chess player in the world, you would have a lot of trouble. Okay, this is not one of these assignments you can sit down and make if-then statements to solve. You need to use a machine learning algorithm, which is focusing on unlabeled computers to perform tasks without explicit programming. So to develop IBM Deep Blue, the engineers over there, they used a mechanism where the chess would play itself over and over again. And it defined a way for the machine to learn and iterate and get better, to the point where now, if you sign up for chess.com, you have to sign an explicit waiver saying that I will not use computers because they have become better than humans in every way. Extending that a little bit more, we have the very, very tough thing. So you're looking at an Amazon Alexa, and that is that skin cancer detection service that we saw before. It's a subset of machine learning based on deep artificial neural networks. And that's one of those terms I'm going to ask you to hang on for a bit, because we're going to be working with deep artificial neural networks for a long time. Okay, it's one of the foundational tools we're going to be using throughout this course. So at this point, transferring speech to text, which is what Alexa can do, and then taking those texts and transforming that into something. If you say, Alexa, turn off the lights, transforming your wave signals from your mouth into something that the computer can use to actually turn off your lights is something that is impossible to do typically. You can't sit down and make if-then statements to solve a problem like that. You have to try your best to put a human brain or a human brain-like system into a computer and teach it. Okay, so our goal is to move away from designing algorithms by hand, traditionally, stuff you've done before for sure in all your classes, to making the computer solve the problem for you, which is what we're trying to define with these deep neural networks. Okay, awesome. So what are deep learning algorithms good at? So it's good at getting information about difficult to parse data. Okay, so at the very top, it's very difficult to parse audio MP3 formats. If you go to an MP3 file, it's hard to tell what to look at, but deep learning algorithms do a very good job at taking that and parsing information about it. Okay, making decisions in complicated fields with human-like precisions. Now we can put these deep neural networks in computers and perform human-like tasks very high to scale it. If you want to diagnose a lot of cancer, let's say you have 1 million pictures of cancer cells, it's very expensive to hire enough doctors to be able to look at all the cancer cells and say that's benign, that's malignant. You can make one computer, put it on a big GPU, and get through all of that in an hour. Okay, so deep learning algorithms learn correlations between complex input and output data. So the things we've looked at before, you can look at waveforms from, we can look at wave signatures from MP3 files and try to transfer that into something that Alexa can do. Okay, so in general, the thing that deep learning algorithms are the best at, performing complicated tasks that you have an abundance of data in. And with such a general definition, you can see where deep learning algorithms are applicable universally. They're very good at challenging different fields because they take onto the field and they learn different parameters in that field very efficiently without a lot of human intervention. So you find them in robotics. There's deep learning algorithms to try to tackle climate change, information science, text-to-speech technology, which is what your Alexa is doing or your Siri is doing, human-like chatbots, medicine, there's self-driving cars, improving industrial plants. And you can see how universally important deep learning is in the future. And that's one of the reasons why this field is exploding so much. So just a little bit of preface on neural networks. We're going to talk about this a lot more next week. Next week is our Introduction to Neural Networks class. But you can really see why I'm talking about deep neural networks is really trying to take the human brain and put it as best we can into a computer. What you're looking at the bottom is a artificial neural network. And on the left is an artificial neuron. And neuron should be a familiar term because we take it directly from biology. In your brain are neurons. Putting them together, we have a human brain. And if you guys aren't aware, the human brain just so happens to be the most complicated thing we have found in the entire universe. We have a very hard time looking inside the brain and prodding towards it. I think we have some people upstairs trying to get into the class. Okay, so if you get them, that'd be awesome. Okay, yeah. Okay, so yeah, I'm gonna continue and I'll catch them up later. So we can see directly, very directly, neural networks. They're both biologically inspired. And the important thing is they're both teachable. So that's a topic we're gonna be tackling throughout this entire 6 weeks of this course, is teaching these deep neural networks to do some pretty awesome things. Both have the goal of taking input data and transforming that into valuable output data. We're gonna be talking about it a lot, especially today when we start coding. That's one of the fundamental things we're gonna go at. So as deep neural networks get better and better, they're able to do more complicated tasks that were once only possible for the human brain. So if you guys think that I'm sure in the news media, okay, awesome, we have some people coming in. In the news media, you see the word artificial neural networks, you see the word machine learning. How's it going, guys? Nice to see you. Thank you so much for coming. I can catch you up a little bit. You only missed a little bit. Okay. You hear the term artificial intelligence, deep learning, machine learning all the time. They're reason they're buzzwords because they're doing awesome things right now. We're doing things that we haven't been able to do. Google is using it as a tool to perform some amazing things. And I dare you guys to wait 10 years and see what it's doing in the future. We're going to be tackling a few different neural networks, and they're designed for different purposes. Okay. So week 2 to week 3. So that's next week and the week after, we're going to be doing neural networks. Very classic deep learning technique. You can do some really cool things with them, and I'm excited to go over it with you. And then we're going to work on some imaging. So convolutional neural networks is neural networks designed specifically for visual imagery analysis. In this example, you can see on the left, they are taking input pixel data of a handwritten number 2, and they're trying to label that as a number 2. So if you guys have ever used online banking, nowadays you can look at checks. You can write your name, you can write how much it is, take a picture of it and send it to the cloud, and CIBC is going to give you that money. It's using the same techniques. They have to figure out how to transfer writing into actual labels. So that is a very profound, very interesting field, and something that we're going to do very similar. Recurrent neural networks. Recurrent neural networks designed for sequential data. Common uses are analysis on language. So that is going to be our final week, our last week, week 6. We're going to go through recurrent neural networks, and it's going to be awesome. In this example, they're taking a movie review. It says, this movie is not good. Very simple. You can make it a little bit longer as well. But what they're trying to do is label that as good or bad. Because if you were IMDb, you're going to get a lot of comments saying, I really like this movie. I didn't like this. This and this. Or maybe they get neutral reactions. And you want to convert that into numeric representations, where 5 could be an amazing score and 1 could be a very trash score. Awesome. Okay. So how can you learn how to make deep algorithms? That is why all of you guys are here, okay? So you are an undergraduate and you are trying to get over to the world of deep learning. That can mean different things for different people. Maybe you want to be a master in deep learning. Maybe you want to learn how to use it for your own sakes. Maybe you're going to be working in a company in the future that will employ deep learning networks. Maybe you're not in charge of training them, but you want to deploy them and you want to know how they work fundamentally, okay? So there are a couple routes. The very classic, very desired route that a lot of deep learning scientists want you to do when they're looking for jobs is going and getting an artificial intelligence graduate degree. And the first thing I got to say is it is a fantastic idea. Okay, this is currently what I am moving towards. I think it's a great program. It can really teach you the ins and outs of the field and get you going and really get your hands on doing something really, really cool. But the issue is that is not an acceptable path for everybody. There's a lot of people who will be locked out by this path for very good reasons. Okay. Typically, when you're an undergraduate, for the first 3 years, they teach you how to program. They'll teach you how to make websites. They'll teach you how to make algorithms. But only until the 4th years will you really start taking optional machine learning classes. So by the time you're there, the majority of people will have in their mind what they want to do in the future. So they won't even consider artificial intelligence or deep learning. If you're going to do a degree, you either get the degree or you don't. It requires a massive life decision or nothing at all. Okay, so that is a very scary thing for a lot of people, and that's why it's not accessible for everybody. There's a large amount of math and statistics as well. And deep learning and math should not be tied together. You can be a deep learning scientist without having to know multivariable calculus, but that will be demanded out of you if you're doing a graduate degree for sure. And not everyone wants to continue academia. Okay, so as it is a great idea, it's a great program. It really is, it'll teach you a lot. It's not feasible for everybody. So traditional solutions is you can take an online deep learning course. And these deep learning courses are designed to take you and maybe inspire you to take a degree. Or maybe you take these online courses and you figure that's where I want to be in deep learning. And that is your world of deep learning. I've taken a bunch of these, the two biggest ones I've taken, and they're great programs. Andrew Ng is a very classic. Thousands of people have taken that online course to learn how to work with deep learning. And it's a great course, also deep learning AI. And I recommend each and every one of you to check it out, maybe in the future. But once again, there are some walls to that. I've taken those. There's fundamentally a high use of mathematical theory. If you're taking any of those big courses, they work from the bottom up and they work from the math out. So they start and they look at the theoretics very heavily. And that is not applicable for everybody. Not everyone can use that. There's a list of prerequisites, and those prerequisites are not very nice prerequisites. There's a high use of multivariable calculus and statistical theory, which is a lot for someone who is maybe in first year or second year or straight out of high school who wants to start working with deep learning, but they can't get there. And there's just a lot of information. They'll teach you from the bottom, and machine learning is a hard, complex, big field if you look at it as an entirety. So I really recommend you guys taking a snippet and working with the algorithms and then moving from there on. And that really is where BrainTank Deep Learning comes in. Our motivation is to really try to take away a lot of these barriers and let everyone work with deep learning. So minimal experience. We ask that you guys maybe know how to code a little bit, but even so, we're just going to work together. It's very based on hands-on algorithm development. You guys are going to make a deep learning solution today. Okay. We're going to get right in there, see how it works with hands-on experience and get it done. We're limiting the amount of mathematical and statistical theories, and we just want to get you into deep learning. Our goal at deep learning or at BrainTank Deep Learning is to really let you guys take your first step in and make your decision from there on. So in the future, you can maybe extend your knowledge with taking some of those math-heavy online courses. Maybe that you want to get a degree after this, or you can take this class and be happy, and you can create your world of deep learning around there. We are going to give you very real, practical, understandable methods to making deep learning algorithms. And so by the end of this course, in week 7, when you're already done, you guys will be able to sit down at a computer and tackle a solution of your choice using these deep learning techniques. So we're going to get you to take that first step, but it's going to be a big step. So be prepared. So here's one of the sticky situations. And one of the biggest walls you have to overcome if you want to get into this field is how you actually physically can train these deep learning algorithms. And I have a good news or I have bad news, depending on the type of person you are. The answer is math. Okay. Fundamentally, from the bottom down, I've talked about this a little bit. Fundamentally, if you look under the covers, deep learning and math are really the same thing. It's one of the same thing. They're very interchangeable, and it from mathematicians came deep learning, and then it transitioned to computer science a little bit later. There's academic publications in the 80s that really define them, and it was a lot of pen and paper and a lot of calculus. So what you're looking at right now on the left is some of the linear algebra that is required to train these algorithms. Some of you, if you guys are familiar with deep learning or machine learning, you might have heard them a little bit. Gradient descent is a very classic technique. Back propagation, you're looking at a lot of partial derivatives, a lot of pretty theoretical stuff. And if I wanted to sit down and teach you guys how to the ins and outs of all that math right there, we would require another 6 weeks, and I wouldn't give you the full prospect. So instead, we are going to provide ourselves a little bit of a layer of abstraction. We are going to be using something called Pytorch. It's a Python library, and it does a fantastic job of doing the calculus for you and doing the tough part for you. So from this course, we are going to teach you how to make deep learning algorithms and use the tools to make real solutions. But we won't give you the full analysis of quite what's under the hood yet. We're going to encourage you guys to learn that in the future, but let's get your hands on it before, okay? A little anecdote I like to see is when I first learned programming, I'm sure every single one of you first learned programming, you guys did it in a class where you were typing away on a keyboard, maybe Python. Any of you guys, where did you guys learn? Like, what language did you use, or how did you learn how to program? Sorry? 1300. 1300. CIS 1300. That's a perfect example. C programming. Yeah, perfect. Exactly, right? It's strange of you that you didn't say you started with soldering circuits together, because it seems like you guys skipped a lot of steps. If you want to actually learn about computer science and start from the bottom up, you guys should have been putting together your own half adders and full adders and the building up. You guys should have been programming in assembly long before C, right? But there's a reason we start programming in higher level languages and then after giving your space to work down. It's the same thing we're going to do right now. We're going to learn how to make deep learning algorithms, do it in a very cool, intuitive way. And yeah, I'll give you some time to look under the hood if you want to in the future. Okay, but we're gonna code on that layer of extraction. Okay, so Pytorch looks a lot like this. It is Python code. I know I talked to some of the people in the front. They have some experience with Python. Maybe not. If not, we're gonna code together, and you guys are gonna pick it up very fast. Okay, if you guys know how to code in one language, you like to code. You know how to code in all of them. Controversial opinion, but it'll be easy for you to pick up for sure. Okay, so a little bit of bookkeeping stuff. What is BrainTank going to look like? Just so you guys understand. Every week, we will address a challenge and use a deep learning algorithm to solve it. We are going to address a challenge today. It's going to be the very next thing we do. This course is a code along, meaning we will all code together, and I'll give some information about how we're going to set that up and how we're going to do it. The three main topics we were going to cover are neural networks, convolutional neural networks, that's with images, and recurrent neural networks, which is with words. Okay, it's the two big fields are called deep vision, your eyes, and natural language processing. So those are two ideas we're going to tackle. It's going to be fun doing those. Concepts will build upon each other. You must go all to the classes to get the full experiences. But these lectures are all going to be recorded, and the information is all going to be public. So if you miss a class, it's okay. You're not behind. Okay. Coming to all the sessions, you will get a BrainTank Deep Learning certificate, which is great for LinkedIn. You'll be able to post it there or on your resumes, and it really tells employees that I have used machine learning on a very real basis. I've trained algorithms and I can deploy them, which is a skill that employers are looking more and more to in the future, especially big attractive companies like Google and Tesla and all the stuff you want to work at. Okay, perfect. Okay, so at the beginning of the slide, I talked about saving lives. So from BrainTank, saving lives with cancer cells, that's something that we are going to tackle in week 4. It's convolutional neural networks and classifications. These are the type of problems we're going to tackle together. These real solutions may seem way out there, but even first-year students, second-year students at the University of Guelph, we can solve these problems together in a very straightforward, intuitive way. It's going to take some time to learn. You're going to have to reconfigure your brain from traditionally programming to deep learning. It's a very different field, but it's something that we can tackle and we will tackle together. So Tesla, saving lives on the roof, that's just an application of something called object detection, something that we're also going to tackle together. Awesome. And then very last, protection of the truth. You've seen it. I've talked about recurrent neural networks. That's what we're doing with it. Okay. It's a form of text classification. Okay. So perfect. That's our introduction. I'm only going to have an introduction week 1. So week 2, we're going to dive right into the problems. So here we are. And I apologize for having these up right now. It's an issue with the display. It'll kick me out if I don't. But we're going to talk about the problem. Let's dive right in. So week 1, here is our problem we're going to be tackling together. It's called cows getting deep. We are presenting at the University of Guelph. I had to add a little bit of a University of Guelph flair. Okay, so here is our problem. Okay, the University of Guelph Agriculture Department is looking to buy 3 new cows for a study. 1 small cow, 900 pounds. 1 medium cow, 1,050 pounds. And a large cow, 1,200 pounds. They need BrainTank to develop a deep learning algorithm to determine the price they should expect to pay for each cow. They give us a chart for all the previously sold cows in the market. Okay, so this is the data we were looking for. These are all the cows that have been sold in market for the past year and their weights and how much they cost. Okay, there's a correlation between how big the cow is and how expensive they are. So we are going to try to develop a deep learning algorithm where you can input a weight of a cow. They want to buy a 900 pound cow, and they want to see how much they'll expect to pay. So in other words, our job is to do something like this. Create a line. It's a linear regression problem. You might have seen it in the past. It's a very classic artificial intelligence problem. And we are going to learn how to put a line right there using deep learning techniques. So with that line, if we have a 900 pound cow, we can determine how much we should really be paying. Okay, awesome. So the solution, we are going to go back to grade 9. Hope you guys are excited. I know some people in the Zoom chat. I know my dad is in this call trying to learn how to do some things. So his example, him going back to grade 9 might have been in the 70s. So it's going to have to go right back. Hopefully you still got the memories there. But grade 9, we're going to go through y equals mx plus b. It's a linear correlation, okay? In a field called linear regression. We are going to try to transform the weight of the cow. We're going to use a slope coefficient, multiplying it by m, and then adding a vertical transition to predict the price of the cow, okay? Now, one topic I want to talk about right now are these red, okay? Every number in red for the rest of this course, those are going to be our parameters, and that's an important topic. We're going to be talking about that a lot, okay? So parameters, m and b are the model's parameters. By finding the best values of these parameters of m and b, we can create a well-performing model. By finding bad values, we will create a poorly performing model, and I'll show you exactly what that means, okay? Here we have an m value of 0.5 and a b value of 1,000, and our model does a very poor job at predicting how much cow should be. In the middle side, we have 0 and 0, another terrible example. You're not getting much information from there. So our job is to find the m value and the b value. That gives us a really good correlation like you can see on the right, okay? So we are using deep learning. Let's start talking about that, okay? We're gonna be talking about the 3 tenets of deep learning, okay? And you see at the bottom left, there's a little star there. How cute, okay? It is because this is a very important topic, and we're going to be talking about this for all 6 weeks, because fundamentally, the stuff that they're doing at Tesla, the stuff that they're doing at Google, every academic publication you can see fundamentally uses data set, model, and loss. It is the tenets, it is crucial with deep learning, so we're going to be using it every single week. So our data set, it's a set of data, wow, that has information that we can use to teach the model how to perform better, okay? It is the fundamental information we are going to use to teach our model. In our example, bam, there it is. It is our data. We are going to be using this data to make our model better. Now, here's where it gets really interesting. The model, okay? This is what a lot of people talk about in the news. These are the things that can perform really interesting things. Our model in every single case, from Tesla to what we're doing right now, is simply a mathematical function or equation that takes an input and creates a desired output. It is defined by its parameters, there's that term again, which are numbers we train/change to get a desired result. So our model in this very straightforward example is something you've seen before. It is our y equals mx plus b equation, okay? We have 2 parameters in this. Fundamentally, it's the same type of concept as a lot of those more deep, interesting things, except we're using 2 parameters. And for a lot of the academic publications I've looked on, we've used millions, okay? But we'll get up to there. We'll get up to there. So in this example, our parameters, like I said before, is m and b. Now loss, this is a little bit of a tricky subject. A lot of people, when they're first learning about deep learning, get a little bit confused about the loss, but it's something we're gonna go over a bunch. It is a mathematical equation, another equation, to measure how well/poorly your model is doing at completing a task. We're going to be using something called the MSE, or the mean squared error, okay? We're going to dive a little bit more into what that means, but fundamentally, that's what we're doing right now. It's called the MSE. Awesome. So the deep learning flow, another star on this slide, so that must mean it's important. We're doing it over and over again, okay? I'm going to talk about this. I'm going to go over this a bunch of times. If you don't immediately understand it, great, because you're not supposed to. We're going to be talking about this topic quite a bit in the upcoming weeks. So just sit back and try your best to understand it. We're going to be elaborating it a lot in the future. So the number one thing you do every time you define a deep learning solution is you initialize a model and randomly assign your parameters of value. Okay, so randomly assigning these parameters of value, you're going to start with a very poor model, a very stupid model. It's not going to be able to perform your task very well. So the next step is to try to get in and train it. You'll grab a single entry from the data set, an input and a ground truth associated with that input. In our example, it's very straightforward. We have a cow's weight. So for example, if a cow is 900 pounds and its price, which is $4,000, that is our input and our desired output. And we're going to use these values to train our model. Okay, we will take that input, which is 900 pounds, and we're going to feed it through our model, and we will get a prediction of the output. Okay, and we can compare those. So we have a bad model. Let's say our model is defined at 0, 0. It is going to predict that a cow that is 900 pounds is worth $0. Does not make sense. It's a very poor encapsulation of the data. So we are going to compare that to what we got and what it should have been. So it should have been predicting a number around 4,000, which is what we have from our data set. We will pass those two numbers, our predicted value and our true value, into a loss function, which will measure how poorly it guessed. We're going to give you some hands-on examples for sure. And what you do is you'll get a number, and that number will be very large if your model is performing very poorly. So if you have a bad model that cannot encapsulate the data, it's very stupid, you're going to have a very, very large number. As your model gets better and better, your loss is going to be less and less. So you want a low loss, very easy. If you're losing a lot, you're doing bad, essentially. And now here's the tricky bit, and also the very straightforward bit if you're using our Pytorch online data set. You will just give your loss to the optimizer, and the optimizer will act almost as a friendly robot who will walk into your model and change those parameters almost magically to get better results, right? You don't have to do a lot of thinking. You don't have to set up code and really think about how to tackle the solution. You can pass it to the optimizer and it'll go in and do a lot of the work for you. So it's magical. And that's how we can train very complex sets of data and use big image analysis and do all the stuff with Alexa and self-driving cars, which is very unintuitive for humans to sit down and code. But the machines are very good at it, is because the optimizer can come in and optimize the parameters to lower the loss, and the lower loss is better. And then fundamentally after that, you just repeat steps 2 and 5 many, many times for the entire data set. And slowly it'll get slightly better and slightly better and slightly better as you learn, much like you're studying for a test. You will see that eventually you'll just get smarter and smarter and smarter until you reach a point in convergence where your model can predict the data very, very well. So let's get on some hands-on understanding and a little bit of graphics so we can understand. We are going to grab the first part of our data set. So we can see in that table, those are all of them. We have 500 data points. It's ripped directly from the graph. We have 500 data points. I'm only going to display 5 right now. And we have a cow that's 942 pounds, and its predicted cost is 4,724 Canadian dollars. We will initialize our model with random values. Right now, our model is initialized with as 0.5 for the value M and 1,000 for the value B. It's not going to get us great results. And what we can do is we can pass in our input data, like I said before, the 942 pounds into the model, and we can have a result from the model and compare that to what the truth actually is. So you see this blue, that is what the model should be close to. But because it's 942's weight, it goes into the model, it multiplies it by 0.5, adds 1,000, and we get the value 1,471. We can see from this graph that if you have the parameters 0.5 and 1,000, you're doing a very poor job, which makes sense because we randomly initialized this model. There was no real sense to making these parameters these certain values. So we have to improve upon that. And how we're going to improve upon that is, if you remember, passing it to our loss function. So our loss function in this case looks like this. You take the result over here, you subtract the ground truth over here, and you square it. This is the most math we're going to be doing today. It's the most complicated math. One thing I want you to keep note of and pay attention. Our goal as data scientists is to have our result be similar to our ground truth. That is what we are pushing towards, we really want to achieve. So if we look at our loss, if our result and our ground truth are the same value, so our model predicted perfectly, it's very smart, very, very smart. And the ground truth is 4,724. And our result that our model predicted is also 4,724. Very smart. If you pass it into the loss function, it'll be 4,724 minus 4,724. And our loss will be 0 squared, or just 0. So if our model is doing very well, we will get a low loss score. But our result and our ground truth are very, very different. So when we run our loss function, instead of getting a low number, we are getting something in the 10 millions. How's it going? You can sit down anywhere. we are not performing like we should. Okay, so we are going to go down and we can take that loss. Remember, our next step is to simply pass that to the optimizer. I'm going to have the optimizer in orange for the rest of the class, like my parameters are in red, because it is another one of those topics that can be a little bit tricky. But what we literally do is we pass our loss and just give it to the optimizer. And it's going to be using a lot of calculus, something called back propagation, which we won't dive into much about. And it'll literally use that, take that, jump into the model and adjust those parameters so the loss will be small. Its job is to try to reduce the loss. And remember, if we reduce the loss, our model gets smarter intuitively. So it'll go into those and it'll change those M and B values. So once they were 0.5 and 1,000, we're getting better results with a M value of 2 and a B value of 500. And you can see in the graph right below that it is getting better, which once what looked like this is now this. It's getting slightly smarter. We can iterate this over and over again with the rest of their data. We can check it over again. We can put in, instead of 942, we can put in 832 pounds and our ground truth of $3,657. And we can run it again. Our result that our model predicted is $2,164, which you can see is a lot closer to the truth than it once was. We're going to put those into the loss again. And instead of getting 10 million, a very high bad score, you're getting a lot of losses there. You're getting 2 million, still quite a bit. Your model is not very great right now, but it's getting better and better and better and smarter as we keep going. You can pass that into optimizer again. And now it's going to go into the model, and eventually over and over again, if you iterate thousands of times over a bunch of data, I'll tackle that in a little bit, okay? You can see that our model can get very smart, and we predicted the data very well on the bottom. You can see right here. Okay, so that is our goal that we're going to tackle right now. The two things I want to talk about, I talked about this a little bit before. I want to reiterate again because it's a difficult topic. Our loss function in this, we're using mean squared error. We'll use a different loss in the future for different applications. But right now, the mean squared error, we just take the result and the ground truth, and it is a mathematical equation to measure how well and poorly your model is doing at completing a task. The loss function is to be minimized, which is what the optimizer's job is to minimize the loss. That is to say, the model that produces the results that create the lower loss score is the better model. Like I said before, if the result and the ground truth are the same / similar, L will approach 0, which is good. If they're very different, it'll be high. And our job is to create results that are similar to the ground truth. Awesome. The optimizer. The optimizer talked about before, complicated mathematical function that is able to figure out how to change the model's parameters to create better results in the loss function. The optimizer is based on very hardcore calculus, and we will not be talking about it in this course. We will teach you instead how to use it. Like I said before, treat it as a friendly robot whose job is to solve a task. Okay, awesome. We got through all of the boring stuff, the PowerPoints. Let's get coding. So everyone, if you have your computers, whip it out. It's going to be very straightforward. I'm going to teach you guys how to do it. All you guys need is an internet connection. Okay. I know before I talked about using a Linux kernel, I actually spent quite a bit of time last time to reassess some things. And we're actually going to be using something online called Google Collab, which I just don't want to show you guys that. We're going to be using something called Google Collab, which is Google Collaboration. It's a tool for deep learning scientists to develop algorithms. And it is a great tool. Okay, so we are going to start off by going to github.com. I'm sure a lot of you guys have used GitHub before, /braintank deep learning. Okay, just like this. And you should get a page like this. You see this, you're doing great. Okay, github.com /braintank deep learning. Perfect. Let me know if we're all there. Ground truth average of prices. No, so to answer your question, Sarah, right now that we have a second, the ground truth, there's a bunch of ground truths, and it is from the data set. Each input data, you're gonna have an input and an output. The ground truth is the true label. So for example, looking at our data, we had a big graph. I can bring that up again. One right here. We had a data set that looks like this. we're inputting the cow weight and our output is the cow cost. The ground truth is, it would essentially be the cow cost, which is predefined before, and it is labeled to be good. But we're gonna talk about it a little bit more. It's more easy to go over intuitively, especially when we start coding. You guys are gonna get it down for sure. Okay, week 1, jump into there. Okay, you should see something that looks like this. Let me know if we're all good. Everyone's good here? Okay, awesome. github.com/braintankdeeplearning. And you're just gonna go to code. It's very easy. If you guys know Git, there's different ways to do it, but we're just gonna keep it simple and we're just gonna download the zip file. And you can open it or save it. I'm gonna recommend opening it. So we're gonna go, just to reiterate, you go to code, this bar right here, open it up, download zip at the bottom, very easy. Once you have that downloaded, you can open it up. Your file should look something like this. Okay. If you open it up, extract it, put it anywhere you want. I'm going to put it on my probably desktop. Desktop, perfect. Actually, I have it already, so I should replace it. But there you go. Now you have it on your desktop, and it should look something like this. It's a folder that has some files that look like this. Perfect. The really, really important one, so we all have it here. Hey guys, big thumbs up. Perfect. The important one that we're looking for is something called week1.ipynb. Okay, awesome. So if you have that one, you're good. Next step. If you go to collab.research.google.com, or if you just look up Google Colab, it'll be the first link. And you'll get something that looks like this. So Google Colab or research.google.com. This bar is in the way. I'm going to move it. There you go. So you can see it. I'm talking about this right here. Okay, let's see if anyone's in the chat. Awesome. Cool. Should be quite straightforward. Collab.research.google.com. And if you make a new coding page, you'll get something that maybe looks like this. Okay. If you have file up here, you're going to click file, go to upload notebook, browse it, and then wherever you download that file, if you have your week1.ipbyn, so I have it on my desktop, go in there. If you have that file, open it up. Okay, perfect. And now it's here. Sometimes it asks you if you want to leave the page, I found. Just say yes. It works perfectly if you do that. So you should have something that looks like this. A little bit of code. Your screen might be white. Mine is in dark mode. I know a lot of you programmers like dark mode. So if you have this, you're doing great. So
Giving me an error.
yeah, let me see.
Ooh.
I don't know what else. Are you on?
Maybe I'll find out.
Okay, you can show me that. Yeah. If not, you can even try different browsers. Okay, so everyone in chat, if you have a problem, this is the time to talk about it. Okay, awesome. But we're going to move forward. The first step we're going to do is we're going to run this little piece of code, Git Clone. It takes a little bit of time the first time. And if you get a message like this, you're doing great. You just have to hit that arrow right there. If you want to check over, if you click this files, you should now have a folder that says week 1. Great. And that has a lot of the necessary information we're going to code with. So you see this cowcost.csv. If you double click on that, you can see this is actually the data set we're working with. That was the graph. There's 500 different cows with the weight and the cost. And this is what we're going to use to train our model. So it's very important we have this downloaded. It also has a couple of files to help you out. I have something called Pytorch help. Just sat down and wrote. It covers all of the trickier topics in week 1. And if you want to reference it, it's there for you to check out. It'll cover a lot of the hardest parts. Perfect. Yeah. Error. Perfect. Actually, yeah. So we'll go over that. If you have something that says fatal, blah, 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 something week one already exists, that's completely fine. It just means you already downloaded it. So maybe if you clicked it twice, that's totally fine. As long as if you go to this folder right here on the left and open it up, if you have week one there, you're perfectly fine. Yeah. So that's a Git error because we're Git cloning. If the folder already exists with this name. Yeah, no worries. So the second thing I want to talk about is I have a couple of helper functions. I developed these just to use in this coding. You don't need to edit them at all. The first one is just going to give you a visual representation of a lot of the data. We're going to be using it in a bit, and I'll show you how. And the second one just reads in the data and puts into a nice format for us to use. Okay. I want you guys to also click run on that, because if you don't, then the Python environment won't be able to pick up on it. So just run it. Nothing will produce, but if you don't, you're going to run into some errors in the future. Okay. So there you go. It just ran. I got no output, which is perfect. That's exactly what you want. Another final thing I want you to run is this. Here is our objective, our small cow. Remember those? Small cow, medium, large cow? Here are their weights. And we were trying to figure out how much we want to pay for them. So we're going to get back to that. That's how we're going to solve our solution. Awesome. Great. So now here is the real meat and potatoes. This is where we're going to be coding. This is the model. And we're going to be coding all on this block. So if you click on this block, you can be coding right here. For example, if I print hello world right underneath here, awesome. Should be working. If everyone's got something that looks like that, that's perfect. I know a lot of you haven't used Python in the past. So the one thing I want to talk about is the indentation. This is a function, for example. You define a function, and instead of having the curly brackets, it ditches those. So something that looks a little bit like this, they get rid of those and they just use indentation. So it's something really easy. You'll learn to it very fast, but it might be a little bit confusing initially. Awesome. So first thing I want to talk about is Pytorch. We are actually importing it at the top, Pytorch. So now we can actually use it. That's what this import torch statement does. So what you can do in Pytorch is if you write torch dot, it gives you all of these amazing mathematical tools. And in fact, that you can't actually look at all of it. It only goes up to B, because it runs out of room on the list. There's so many great things you can do with it. The big one's torch.nn. If you do that, dot, what that is going to give you is a lot of the neural network stuff we're going to be doing. Okay, so convolution, remember CONV, I talked about convolutional neural networks. We're going to be using these a lot. Embeddings, that's a topic we'll be covering in recurrent neural networks. There's a lot of great tools that will help you out. And we're going to go through those together. The one thing that's a little bit tricky is instead of using traditional numbers in Python, you can define a variable like x equals 1, and you can print it out, print x, and you'll get something that looks like this. With Pytorch, because of the mathematical properties behind how this works, you have to use something called torch tensors. So instead of defining a number, you define a number like this. So x equals, oh, not tensors, my mistake. Torch.tensor, okay? Instead of using 1, 2, floats, doubles, stuff like that, we're going to be using torch tensors, and there's a mathematical component around there. They're very straightforward. The only real difference you guys have to worry about is in the initialization. So we're initializing a variable right now, but let's say you have another one, torch.tensor 2, you can treat x and y as numbers. So if you want to print x plus y, you can just do that. There's nothing special behind them. You treat them completely as numbers, and 1 plus 2 equals 3. How's it going? Yeah.
What's the difference then between doing x equals 1 and x equals torch tensor?
Okay, yeah. So what's happening right now with the torch tensor, if you look behind it, it has a special function behind it. It is a class. If you guys have worked with classes all in Python, and it has a bunch of essentially what Python, they're equivalent of instant variables that will record something called the gradient, which is a math term. And the gradient is what is required for the optimizer to use to change these parameters to make good things. So there's a lot of things going on behind the scenes, but in front of the scenes, it's basically the exact same. So that's a great question. Yeah. How's it going? Yeah. Okay, so those indentations, you gotta move them all the way. Yeah, awesome. Thank you for helping out. Okay. Yeah, so you can multiply these together. Same idea. 2 times 1 is 2. You can divide them. You can do everything you can imagine you want to do. They are quite amazing. They're quite straightforward. You guys are going to get used to working with them very easily. It's great. You can also add. You don't have to use 2 tensors to add each other. You can add ints directly to the tensor. So x plus 5. We're taking this tensor and we're adding an integer 5 to it, and we get the same result. We get 6. They're really straightforward. The thing that we'll get to in the future, and it's really getting to the word tensor, which has to do with if you've done linear algebra at all, a 0-dimensional number is a scalar. That's like just like an int, a float. A 1-dimensional set of data is a vector. If you go to 2 dimensions, it's a matrix, and if you go to more, it's a tensor. So this is designed to use a lot of multi-dimensional stuff, and it's something that we're going to tackle in the future. But right now, we're just going to use them as scalars. So if you wanted to, you can do something 2-dimensional. So now we have an array where it has the values 1 plus 2, and we're just adding 5 to each one of those, and we get 6 plus 7. Okay, very straightforward. You guys are going to pick up on it very easily. Great. So the first thing we want to do, remember, the 3 most important tenets of deep learning: data set, model, loss. Let's tackle the data set. I have done a lot of work for you. We're going to want to do data set equals, and remember, we want this at the absolute left. We don't want it to be indented, so that it won't run. We want it to be all the way to the left. Equals, we're going to use the function read underscore data. This is one of our helper functions. Okay, it's this one right here. And we were going to give it its path. And our path we want is week 1 slash, and we want to get our data set, which is cowcost.cfv. Cowcost.csv. So if you do that, and you should print it out, if you have code that looks like this, you should get something that looks like this. We're going to have a lot of data. So here on our left, those are all of our weights. And here is the cost of those cows. And it's this that we're going to use to train. So going back to the question we had before, here are our input weights. And these are the ground truth values associated with them. So the ground truth value associated to this specific cow with a weight of 866, its ground truth value is 3,980. That is what a ground truth value is. Right? We are going to train them, and we're going to compare those ground truth values to what our model predicts. So awesome. Now we have our data set. I'm going to just write down defining the data set. Perfect. Step 1, complete. Now we want our model, data set model loss. Yeah, how's it going, man? Sorry? Okay, yeah, that's a problem I thought we were going to run into. What you want to do is you want to click the helper function and you want to run it. If you don't run it, it won't actually define this function as a part of the environment. And if your web browser crashes or anything, you're gonna have to run everything again, unfortunately. That's one of the downsides to this, but yeah. Now, if you run it, you should see it working out. That is a great question. That's a very common error that happens. So we're defining the data set. Now we're gonna move to the model. So let's defining the model. Here we are. And how we're gonna do it before, I have some help for you already. I did a lot of the dirty work. This is our model right here. And if you remember, our model is y equals mx plus b. We're going to get to that. In Pytorch, how you make a model is you define it as a class. Now, if you guys have taken the second year at all, you guys are going to be moving on to Java and be working with classes a lot. Python does use classes. This is a Python thing, not a Pytorch thing. But they're going to be really intuitive. We're just going to use an init, initialization, which is if you've done Python, it's the constructor and a forward pass. It's going to be very straightforward, and you guys will pick on it soon. So if we want to make our model, we're going to say my model equals, we're going to go up to the name up here, and the name of our class is cow predictor, capital cow predictor, like this. And we're going to initialize it like this. Okay. Anything you've seen in the past, you've probably seen initialization of classes like this all the time. Now we have a object, a cow predictor object. Okay. 2 thumbs up. Awesome. So what happens when we do this is it goes into cow predictor and it initializes it. It'll run, oops, you don't want that. It'll run this function right here. So if we get rid of pass, we don't need that. And say print, I am initialized. Okay, we will see if we run this code. Awesome. It goes into the model, goes into the cow predictor, and it initializes this object, and it'll print this out. Okay. So in initialization, the thing we want to do in initialization in Pytorch is define our parameters. Okay, so that is what we're going to do. We're going to type self dot m. So we're going to define our m parameter first. Self is the Python version of an instance variable. It basically sets a value to the object of a certain value, and we're going to set that to, in Pytorch, we want to use this function torch.nn dot. We've seen nn is very useful. Capital P parameter, and that is how we set up a parameter. It'll tell the optimizer, hey, I'm a parameter, I want to be optimized. And we want to set this parameter of value. Okay, so remember in Pytorch how we set those values? Another torch dot and then tensor, no nn this time. And we're going to give it a value. I'm going to set it up to be 0.5, like your example before. Okay, right? So this is what we're looking at. There's one, oopsie, spelled torch wrong here. One other thing I need to talk about is in this torch.tensor, right next to the tensor, we're going to give it another value. If you look right here, this will tell you everything that the tensor can take in as a parameter. We are going to be using required grad. Okay, requires grad. So we're going to write right next to the 0.5, requires grad equals true. And I've talked about grad a little bit in the past. It is our gradient, another calculus term, but what it basically says for the function is, hey, do calculus on me. And that calculus is what the optimizer is going to use. So we're going to do the same thing for B. Self.b, we have 2 parameters in this model. Torch.nn.parameter. Should look very similar. You should be a little bit familiar with this. Torch.tensor, we're going to set a value for it. Let's set a value of, I'm going to do 0.0. Okay. I also have to say, you have to use 0.0 because in Python, it'll define this as a float and you want to float, and int will cause an error. We requires grad. We'll also set that to true. So they should look very similar. Self.m equals torch.nn.parameters, and then in brackets, torch.tensor. And we're going to set that tensor value to 0.5, and we're going to set the required grad to true. So now we have our 2 parameters. We're doing great. We have our initialization of the model, right? So what we can do is, if you want to look at it, you can say my model dot m, and you can peek out. We have our model, and it is defined. Our parameter is our value of m. We printed out is a parameter containing the tensor, also known as the scalar number, 0.5, and it says do calculus on me. Okay, we are ready to use these numbers in the future. Okay, we can do the same thing with b. B will be the exact same thing. Okay, it's the value 0. Okay, so here we have a model object. Okay, so we have our m and our b. Great. We do not have our y equals mx plus b though. That is the main issue we are running into. We haven't really defined a way of putting these parameters together to create a meaningful output. So what we are going to do is we are going to put data into our model, and we do it like this. Okay, we can call our model like a function, which is kind of amazing for Python. That does it very intuitively. If you want, you can put in the weight. Let's say we have a cow that's 900 pounds. we can call my model 900 just like a function. And we can try to print out that value in the future. It won't give us anything immediately, but you'll see. Okay, so what that'll do is it'll go to this forward function. So our two functions, we have our initialization and our forward. And what it does is our forward function, perfect. Our forward function takes in the value 900 as a parameter, a cow weight. Here's one of our parameters, and it will run it through this function. It'll run this function and return whatever it returns. Right now it's returning nothing, so we get none. But what we can do is we can say cow cost, which is what we want to solve for, equals self.m, which is what we're talking about before, it's our parameter, multiplied by the cow weight, which is a little bit confusingly, it is our Python parameter, it's our function parameter, but it is not our model parameter, plus our b value, self.b, okay? And there is our y equals mx plus b component. And now when we pass it in, we can see our cow weight, 900, it's gonna go into here. Our cow weight is equal to 900. We're gonna multiply by our self.m and then add our b, and we can see the result. And I'm sure you guys can make a prediction. Oh, my mistake. We actually have to return it as well. So there we are. So the function will call and it'll return the cow weight. And you can see it's working perfectly because our function parameter 900, our cow weight we put into it, it goes into this function. We multiply it by our m value, which is 0.5. We add our b value, which is 0, and which equals to 450. Okay, awesome. If we change our b value to be 100, it'll now add 100 to it. So it is using our parameters to solve a problem. We are on the right step. One other bookkeeping thing, and this is something we're going to talk a little bit more about in the future. What I want you guys to do is do self.b times 1000 in these brackets, okay? And I'll talk about this a little bit more why, but fundamentally what happens sometimes with these models is you want to have normalized inputs, which is a topic for next week. Yeah, how's it going?
The forward function that's in the class, so that's like kind of predefined, right? In Pytorch, or no, within the class.
Yeah, so it is under the cow predictor class.
Yeah.
It is used, if you look at the torch.nn model, it inherited some ability, and that's why it works as a forward function. It does some special things there.
Every time we're gonna name it forward.
Every single time. Forward is important. If you use something else,
yeah.
If you call it hello, you're gonna run into some errors, okay? Forward is a special name. Yeah, great question. Okay, but going back to this, essentially all it'll do is instead of having large values of b before, like 1000 or -500, which we used in the past, that can cause some unpredictable behavior. You want to keep those numbers low. So instead of being 1000, if our b value is the value of 1, which is low, we want to keep our b value low. If we multiply it by 1000, we'll still get those desired results. We just have to keep those numbers a little low. Again, we're talking about a lot more next week, so stay prepared. Awesome. So our next step, we are going to look at, great, we have our model, it's ready. We're going to tell our model we want to train you. And how we do that in Pytorch is very simple. We use the function my model dot train in brackets. And now that says my model is going to train. That's one of the things I wanted to do. Perfect, 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 perfect. Great. We're going to go back a little bit, but what we can do right now is we can use another helper function that I made. So the other one, remember up here, display data. We are going to check out and see how it's working. If you do display data with the brackets, we're going to pass in our data set. We're going to pass in our m value, so we can do my model dot m and my model dot b. Give that to this function. If we press that, we should see that we get a little graph, and that's what the function I made does. Is it makes this cute little graph, and we can see how our model is doing. So with the parameters of 0.5 and 0, we're doing very, very, very poorly. If we edit this out, instead of doing 0.5, we could do, let's say, 5.5. Perfect. Now we're getting a different result. We're using different numbers. If we do something crazy, like 100.0, we can see that reflects on the data. Our model is now doing very, very differently. Okay, so let's put that back to 0.5. Here is our starting point. Okay, we are going to next. Yes, let's go. What are you looking at?
Yeah, the indentation. I don't know, maybe the text has spaces.
Indentation. Okay, Sarah, do you want to look at the Dino? Okay, awesome. Appreciate that. Okay, next we are going to go through the data set. So we have our data set as a big list. If we print it out, I'll show you just to remind you. We have our data set in a massive list. Looks a lot like this. Okay, so let's take it individually. Remember when we were running the code, we looked at the first data, and then we looked at the second data, and then the third data sequentially. So let's do something, a for loop. So just like in C, we have for loops. In Python, we keep it a little bit easier. We can do for pair in data set. Okay, that's all we have to do, this function, for pair in data set. And if we print the pair, we will see that we are going through every single loop, and it should look very similar to the past. Okay, actually, I should delete this. 1 second. Okay, awesome. Essentially, what it's doing now is, as a for loop, it's going into the data set and it's printing out every single pair. Okay, so our pair is an array. The first value is the weight, and the second value is the cost. So to make it pretty obvious, let's do cow weight equals pair 0, and cow cost equals pair 1. So if we want to go through the data set, I'm sure you guys have done a lot of this in C, and it's pretty straightforward. If we print out, we can print out all the cow weights. And now we have every single cow weight. If we do that with the cow cost, we have every single cow cost, and it'll just loop through the data set and print everything. Okay, perfect. Yes. Yeah, no worries. That's actually a good idea, especially for everyone on Zoom as well. Totally feel free to take your time understanding this stuff and just go through everything. Let me know if I'm speeding a little bit too fast. Like, don't be afraid to shoot your hand up. Yeah, awesome. So I'll go over everything once again. Our model is this class, our cow predictor. We have our initialization of parameters right here, self.m, one of our parameters, and self.b, our other parameter. We're using Torch's parameter function to tell the model that, hey, this is a parameter. And then we were putting a value in it. In Pytorch, we were using our values. They look like this. And this is going to act as a float. Okay, that is what we're doing. In our forward call, this is our actual y equals mx plus b. We're putting it together in one beautiful motion. We take a function parameter, we can give it a cow cost or a cow weight, and it'll try to confirm that into a predicted cow cost. So this is our prediction. This is what our model assumes. And in the beginning, it'll be very poor, and it'll get better and better as it goes forward. Okay, so we're multiplying that by self.m to cow weight, and then adding our linear component. Okay, we have our data set, which is our list of data. We have our model. We're telling the model to train, and perfect. We're good. So we don't really need this display data right now. Awesome. Let us test out our model and see if the results are any good. So we are going to have a predicted cow cost. And that is what our model predicts. So we're going to go to my model as a function, and we're going to pass in cow weight. Okay, so talking about ground truths, this is the ground truth, and this is the predicted. So we can actually talk about that. Instead of doing count, if you want to do ground truth cow cost, and this is our predicted cow cost. Okay, and we can actually see how those compare to each other. So this is the true value. This is what happens in real life, our ground truth. And right next to it, we are going to print our predicted cow cost, and we're going to see how those compare. So for every single example, if we go through it, our predicted cow cost is going to be in a form of tensor. But if you look at the numbers beside it, you can see that our ground truths are usually around 4,000, 3,000, 4,000, 5,000, around that area. And next to them, we're getting a lot smaller values. Okay. So for example, this cow, we were trying to predict the value 4,731, but we hit $596. We're doing very poorly again. This model definitely needs a lot of training. Okay. So how do we train this model? We can remember going back to our other presentation we went through, the slideshow, is we need a loss function, a way of defining how poorly we're doing to compare our ground truth and our predicted cow cost. We need to put a mathematical value. So the one we are going to do is we're going to define a function, and our function is going to be called the mean squared error. So let's define our loss function. So look how nice this is. We have the big three ideas of deep learning: data set, model, loss, right next to each other. Okay, so we are going to use, okay, awesome. We are going to use define. So this makes a function in Python. You might have seen it in C as like int function like this. In Python, we just use define. And we're going to call it MSE, mean squared error. So what we're talking about, loss. And our MSE is going to take two numbers. It's going to take our ground truth cow value and our predicted count value. So we can say true, predicted. Those are our two function parameters. Awesome. And it's going to be very straightforward. If we look at the equation before, we just want to return the value. Okay, inside there, it's the true minus the predicted, and then you square. In Python, if you want to square, they make it very nice for you. You just do two asterisks, I guess, two multiplication signs essentially, and that'll square it. Okay, so going over it again, our mean squared error loss takes in two things: our true, which in this case will be our ground truth cow cost, and our predicted cow cost, which is our predicted cow cost, subtracts those together and squares them. Okay, so reiterating this again, if our model does a good job at predicting the truth, these numbers will be very similar. If you take the two same numbers, subtract them from each other, and then square it, you're also going to get a small number, which means we're doing good. You have a small loss, our model is training well. If these are very different, if our model is very dumb, we're going to get big numbers. And I think you will see that our numbers are very, very different, so we're going to get a big loss. So let's see it happen. Loss equals, we are going to use our MSE now, MSE loss. We're going to take in our true value, ground truth, bam, perfect. And we are going to also pass in our predicted value, bam, awesome. Okay, and let's see what happens. We're going to print out our losses. Okay, so if we do that, oh boy, big numbers. Look at that. So like I was talking about before, here's 11 million, 27 million, 15 million, big numbers. Big problem as well for our model. Our, the agriculture department at the University of Guelph is not gonna be happy with this, for sure. We gotta fix that. Okay, so we have our loss. Do you guys remember the next step? We have our number. Sorry?
Pass it to the optimizer.
Very smart man. We are gonna pass it to the optimizer. So, remember all the complex math I showed you, all those gradient descent, backpropagation methods? We are going to define the optimizer, and it's going to be very easy. Define optimizer. People have entire degrees. We're going to call it optim. Entire degrees about developing optimization methods. And we are going to step over that in one line of code and cover all of that very, very easily. So torch.optim. Okay, here's a tool, and there's a bunch of different optimizers with different names. The one we want is called SGD. It's called stochastic gradient descent. Okay, it's one of the very fundamental types of optimizing formulas. It's very simple. It's not used as much anymore. They have other different formulations, but it's very good for this type of task. Okay, our parameters we want. These are our model parameters. If you want to show all the parameters in the model, we can do parameters or model, or which is, sorry, my model, which is, if you remember, our cow predictor, dot parameters meters, and that's a function. So parameters like that. And then now that's going to give the optimizer the parameters it wants to optimize. The next thing we have to do is give it a learning rate, which is a mathematical thing. And I'm just going to give it to you. For SGD, a very common one is it's 1 to the power of -7, so 0.00001. And you don't have to worry about that too much. We're not going to cover that. I'll just give it to you each time, and you'll be able to see the output of what happens. But this is what we're going to give it. I want to show you what this function does right here. My model.parameters. If we do that, my model.parameters, we can print it out. I'm going to actually get rid of this because it's clogging up our screen. Okay. That basically gives it, what this is a pointer. You use C, you guys should all be C guys. You guys are at Guelph, like pretty much the only university that specializes in C. It's a pointer that points directly to our parameters. So it'll go to the my model and it'll say, this is where my parameters are taken. So by giving that to the optimizer, it's telling the optimizer, hey, here are the parameters I want to optimize. That's what that does. Okay. So just give some intuition of what the optimizer needs to function. Okay. And now this is where we're going to pass the loss to the optimizer. They do it in a different way, maybe a way that you wouldn't quite think super intuitive. But what you do is you do loss dot backward. Okay. So our loss, if you remember our loss when we printed it out, it wasn't just ints, it was that torch tensor thing. Okay. So loss dot backward does a backward propagation, which is a method developed in Canada in the 80s, and it really allows a lot of this stuff to happen. So be proud to be a Canadian, because a lot of deep learning is a very Canadian thing out of UT. But that's what it does. Back propagation. It essentially, what this does is it tells the optimizer, hey, this is how much I want to change it. Hey, this is what the gradient looks like. La la la. Okay, we won't touch on too much. And then to finalize that, to tell the optimizer, hey, I really want you to do it, you're going to do optim.step. Okay. And at the top, one other bookkeeping thing, right? Every single time you run a loop, so right under this loop, you're going to want to do optim.0 grad. That is that grad word again. Essentially what that does is it resets everything. So if you don't do that, you'll get different gradients building upon each other. La la la. Also move a question. Is that the same every time we use the optimizer? In this example, yes. Actually, different optimizers have different recommended learning rates. So if you use stochastic gradient descent, 1e to the -7 is like the classic number. You can deviate them a little bit and you'll get different properties of how quickly things train, how slowly things train. But changing it too much can lead to some uncertain things to happen. And actually, at the end of this, I'll play around with it a little bit and show you what happens. Okay, it's a little bit fun. Awesome. So what we've done, to reiterate, you need this optim0grad.com or optim.0grad function. That'll tell the optimizer, hey, we're ready to give you another example. We are going to create the loss via the predicted cow cost and the ground truth cow cost. If you use loss.backwards, that tells the parameters, how much they want to change, and it'll tell the optimizer, hey, you should go over and change these parameters by a certain amount. And an optimizer.step will say, let's do it, and it changes the values for you. Okay. So it might be a little bit confusing as exactly what's happening under the hood. It's intended to be like that, so don't worry. But what I want you guys to see is how it affects some things. Okay. So what we can do here is, if you print my model dot m and my model dot b, and remember what that does is that goes into your model and it prints out the M and the B values. Before, when we did that, we got 0.5 and 0. We'll see what happens when we do it now. If we run this code, it's going to run a bunch of times. Oh, very, very interesting. It's a lot of data, so you might be a little bit confused by it initially. But what happens, if you look at the top, it starts to change. So the first value, the M value, which was initially 0.5, the optimizer looked at that and said, I don't like that. We are going to print out, we're going to change that to 1.3, and then 1.5, and then 1.9, and 1.996, and keeps going. And each time you run this again and again, it'll change a little bit and a little bit and a little bit until it reaches something. So now, by the end, it gets to 3.65. So if we get rid of this, we don't need it anymore. We look at our printing function. So our predefined model display data. And remember how to do that. We just display data. We pass in the data set. It's not that set, data set. We pass in my model dot M and my model dot B. I want to show you what it looks like before and what it looks like after. Okay. Awesome. So we have two different pictures. At the beginning, our parameters are 0.5 and 0. And at the end, I think they're about, they were 3.3 and 2. And look, you can instantly see that it's much better, right? So it went from very bad, and using this iteration, using this loop we talked about before, we're doing exactly this. This is the exact thing that we're doing in this loop. Just like in this example, we are slowly getting better and better and better until we reach a convergence point, okay? But we can see that this is not doing perfectly. By printing this out, it's not quite what we're looking for. It's a little bit less what we're looking for, actually. So a nice way to cheat for data scientists, we use all the time, is we run through all the data. We train on every single thing in the data. It's like if you're studying for an exam, you went from the cover to the back of the book and you learned everything. So if you want to keep learning, you flip the book over and you do it again. Okay. So the term that I want you guys to get familiar, which is used in deep learning a lot, is you use epochs. So you can do epoch in range 10. And that's basically a for loop that'll go from 0 to 9. It'll go 10 times. So if you print out epoch, I can show you. We also need you to tab that out also. Oh, my mistake. Also 4, my mistake. So it should look like this. You should have 2 indentations now. So this is a nested for loop, essentially, if you used this before. 2 indentations. I'm going to get you guys to print out epoch so you can see the epoch number. And then run this again and see how it looks. Oh, my mistake. The second thing I want you to do is right under printing the epoch is to display the data. And we can see how that improves. Okay, so, the displaying data takes a little bit longer than putting it out. But essentially what happens is the first epoch, this is at the very beginning, this is bad initialization. It'll get better and better and better. We've seen something that looks like this before. This is after 2 epochs. This is after 3 epochs, after 4, after 5, after 6, after 7, after 8, after 9, and at the final, this is the end. And we can see that we've done a very good job at encapsulating this data. So you guys should be very proud of yourselves. Okay, this is how we learn fundamentally. Every single week. Right now, it's been very direct. I've basically coded and I've just told you guys to follow along. In the future, once you guys are a little bit more familiar with Python and Pytorch, it's going to be a little bit more question and answer, and you guys are going to be developing your own solutions. I'm going to be going around and maybe helping you guys out, pointing you in the right direction, but I won't be coding directly for you. But every single week, we're going to do something similar to this. This is how you train something. We're using different data sets, different models. We're going to be tackling problems in different ways. There's different things you're accustomed for. But this is what training looks like. We took our bad model and we asked the optimizer to fix it for us, and it's stepping through it and it's done a really fantastic job. So now to solve our issue, let's get rid of the display data. We don't need it anymore. Yes. Yeah, of course. What does the model.train function do? Great question, Dawson. Really good question. So the model.train, each model has two different functions that you can tell it to do. You can train it, or if you do model.eval, it's a model.evaluate is what it says. If we run this, I'll just show you exactly what it means. We should, oh, actually, I should have kept the printing. I'll show you here. If we do that again, it's not very useful, is it? Oh, that's not right. Oh, still train. There you go. Oh, it's not right. Oh, yes, of course. Okay, my mistake. Eval it won't be very useful in this example precisely, but you want to use it in evaluation mode. So basically what happens is sometimes when you're really developing complex machine learning algorithms, there's certain things you want to do while training that you don't want to do while evaluation. So if you go to your forward function, and let's say you say if self dot, I think it's training. If not, it's self dot train. You can use in your forward loop self dot training, and it can do specific things. So you see us say hello, hello, hello a million times. If you do eval, now your model knows that it's in evaluation mode. It won't perform this function. So it's not going to print training over and over again. So it's not super applicable in this right now, but there will be some times in the future where we're going to want to do some things while we're training that we won't do while we're evaluating. So I haven't really gone directly into what evaluation is, but we're going to do that right now. So it was a great time for a great question. Evaluation is once your model is trained, it's learned everything. Now, instead of studying for the test, we're going to test it. So in our examples, we want to find our small cow cost, large cow cost, and medium cow cost. So small cow cost equals, this is what we're trying to solve. We can use my model to predict it. And what we want to give in is our small cow, which is the small cow weight. So it'll take this number. Remember, if you haven't run this, I'm going to actually recommend you guys click this run button right now. If you don't, you'll run into an error that we've seen before. It'll take 900 pounds, and it'll use my model to convert the pound data, the weight data, into a cost data. And it's a predicted cost data. So we've trained our model, and let's see how it does on the predictions. Small cow cost. Now, mostly because of functionality, I've showed you that it doesn't really do anything right now. But when you're evaluating things, it's a good practice to say, I'm evaluating. So now this will tell the model, hey, I'm no longer training. I'm ready to do the test. Let's see what happens. So let's see what we get for a cow. Oh, we should maybe get rid of this. A little bit not so useful. And we don't really need this either. Okay. So now it'll purely train it. It won't print out any data. You already know that it works. Awesome. So, okay, we also don't need this one. My mistake. It does train. Maybe actually, you know what? Just to show it a little bit off, show you how good the data is. There you go. We'll display it after we train it. So we've trained it. This is called the training loop. It's gone through the training loop. It's trained it. It's produced this model right here. And now we pass it in the small cow cost, $900 right here. And it's going to go up and it's going to produce an output. And that output happens to be $4,089. So going back to our first question, we were asked by the university to make a deep learning model that'll learn how to predict a cow cost from cow weight. It seems like we've done a great job. $4,089 is a great price for a cow, and it's something that the University of Guelph can use in the future. Okay, completing the question, we can do medium cow cost equals the exact same idea. My model, medium cow, and then we'll do the exact same thing with the large cow. large cow, and let's print out all those values to see what they should be. Also, medium cow. I do type quite fast sometimes. Let me know if I'm going too fast. Okay, so we have our small cow cost. Awesome. Just gonna get this real quick. This is mostly just bookkeeping stuff. Make it a little bit prettier. Awesome. So now we have our small cow cost, $4,089. Medium cow cost, $4,759. And our large cow cost is $5,429. I think that's a very good example. So you guys should be proud of yourselves. You guys did it. We made a model and we learned how to do it. And this is a great example of what we're going to do in the future. Okay. So that is your first AI solution. You guys can see how different this is from a typical problem you have probably done in the past. This is not like sitting down and thinking out how to sort a list of numbers. It's very different. It's a different type of use of the brain. And it is something that we're going to elaborate upon in the future. Okay, so that was week one. We've completed. If you have any other questions, please let me know. We are going towards week 2 tomorrow, where we get into something I find especially interesting, and I'm sure you guys will too. We're actually getting into neural networks. Okay, so a topic that is usually saved for a little bit down the road. Usually when you're learning machine learning, you have to tackle a lot more issues before. They'll get through that optimizer, they'll talk about different things, but right now we're going to get right into neural networks, and we're going to use Pytorch to solve a different issue. So tomorrow we're going to dive right into the problem. We're not going to do another introduction, or sorry, next week. It's the same time. You guys don't need to get tickets again. I know we talked about the bit.ly/braintank. You have to sign up. You only need to buy once, so don't worry. Just show up next week. You'll be happy. For some of these people online on this test, if you guys want to show up to the online session, you can email me at either nvinden@uofguelph.ca. I can put that in the chat. Please feel free to message me anytime if you have any questions. If you see me on campus, I'm here a lot. Come say hi. You can email me there or on the Brain Tank Instagram, anywhere really. I'm really thankful for you guys showing up. I've spent a lot of time on this course and I'm excited to keep going. So I hope to see you guys next week. And you guys should be proud of yourself for coming down here on Saturday and learning. Okay. Am I going to post the recording? Absolutely. This recording is going to be up. The links will be on. If you remember the site that you signed up for, I'm going to put a link up there to the YouTube directory. So if you just go to bit.ly/braintank, it's going to give you a link to the YouTube, and it's going to be there. Awesome. Hey Nicholas, really enjoyed your workshop today. Your piece was great. Enjoyed. Okay. Thank you very much. I appreciate that, guys. We're getting very nice comments. Thank you for the link. Great idea, Sarah. Oops, 1 second. We need to email to get the link for the next meeting. No, this is actually the exact same Zoom link we're going to be using for the rest of the thing. It's the exact same link. If you're on it now, you can be on it later. No issues. I want to thank everyone for coming today. Awesome. So I'm going to be here for a little bit longer. I'll keep this on, but that's it for now. Okay, so thank you very much. Cool. Awesome. Great. Thanks for coming, guys. Yeah, thank you. I hope you guys learned a lot. See you next time. Yeah, so I want to remember your name. Faraz. Yeah. Faraz? Gavin? Eric? So awesome. Thank you. I appreciate it. I really hope you guys. Yeah. Thank you very much. How's it going? Nice.
Yeah, so I will send you actually. So this here is the link I'm going to send you. This will is going to put all the videos on here, so every time you get one, and this is going to be the link for that side. So I'm going to email this to you.